Hi, class. This is our video of our lecture for physics on Monday, February 1st. We've just wrapped up our unit on forces, and now we're ready to move on to our next topic of momentum and energy. To start this unit, we're going to talk about momentum, probably in a little bit more basic way and apply it in a little bit more complicated ways than you have in the past. We're also going to include collisions in this, as it gets very interesting. We have some interesting math, interesting physics involved here. So to start with, we're going to use the variable p when we talk about momentum, just like we use t for time and d for distance, v for velocity, a for acceleration. We're going to use p for momentum. And that actually comes from an old Latin word that kind of described the concept. So yes, p just seems kind of odd. Now, I want to start with a little bit about Isaac Newton. And when he was deriving his calculations, his formulas rather, his laws of motion, he was thinking of this concept. He didn't have a name for it, we call it momentum. But to describe what he was trying to get at, he used the phrase quantity of motion. Quantity of motion. So let's think about what that might mean. How much motion does something have? And if we go back and think a little bit about his first law, right, an object at rest tends to stay at rest unless acted upon by an outside force. An object in motion tends to stay in motion unless acted upon by an outside force. So at some point there, we're talking about the amount of motion, right? So how can we describe what that is? And also kind of corresponding to that definition of his first law, he thought of momentum as the tendency of an object to keep moving. Tendency of a moving object, rather, to keep moving. So a little bit similar to inertia, right? Inertia was more the resistance of an object to change its motion. Think of momentum as being the tendency of an object to continue its motion. So we need some way of quantifying how much motion it has. Now, this leads also right into his second law of motion, right, with F equals ma. So if he talks about momentum being the tendency of an object to keep moving, well, let's think about that a little bit deeper. Let's use that triangle, that delta. Remember, that delta just simply means change. So delta P would be change in momentum. And you say, well, how can we measure the amount of motion, its tendency to keep moving? Well, let's look at that quantity. We're going to call it delta P. And let's see how that changes over time. So delta P over delta T. How would that change over time? So we're trying to get a handle on what's that tendency of that object to keep moving, keep that momentum. Well, if we take our definition of momentum, actually I need to take a step back, right? Momentum is a product of mass and velocity. So if we take that definition of momentum, P equals mv, let's spread this out a little bit more. So delta P, the change in P, is equal to the change of mass times velocity over the change in time. Well, mass, at least as long as in our normal everyday world where we're not relativistic, mass doesn't change. So the only thing that can change here is going to be your velocity. So we can pull that m through to the left-hand side of our delta. So we have mass times our change in velocity over our change in unit time. Well, we already know what delta change in velocity over change in time is. We call that acceleration. Right? So m delta v over delta t gives you ma. Right? And then Newton's second law tells us that ma is equal to our applied force. Now, some of you may have seen a poster I have in my classroom. It's right by my whiteboard, and it says, may the, then it has a nice mathematical term, be with you. So the Star Wars fans are going to know that may the, what's the next word, is force. And what my poster in the bulletin board shows is it shows the change in momentum, change in mv, divided by the change in time. Well, that's exactly what we're showing here. The change in momentum over the change in time gives you your applied force. And again, this fits very well with Newton's first law. An object in motion tends to stay in motion. An object in rest tends to stay at rest unless acted upon by an outside force. Well, if we talk about that motion being p, your momentum, then this change in motion, delta p over delta t, That's what we're saying. The tendency to keep moving, does it change that amount of momentum, is directly related to our applied force. So it all kind of comes together, and I wanted you to take a moment and see that, how momentum fits in nicely with Newton's equations. Now, another thing about momentum, we learned earlier this year about vectors, right? Momentum, again, it's a vector quantity. So what do I mean by that, right? It's got a direction, it's got a magnitude and a direction, and the direction of momentum, right, is the direction of the object's velocity. Right? We saw that momentum is the product of mass times velocity. Mass doesn't have a direction, right? But velocity we know does. So if momentum is mass times velocity, it's going to get its direction from the velocity. So let's do a couple simple problems just to kind of get in the mode of thinking about momentum. And our first one here, it says, who has more momentum? A 150-pound quarterback running at 12 miles an hour or a 210-pound linebacker running at 12 miles an hour? Well, the first thing I want you to see here is both of these have the same velocity. Both are 12 miles per hour. So which one's going to have the most momentum? It's going to be the one with the bigger mass. Right? The one with a bigger mass, right? So the linebacker he has a bigger mass, or she, then the linebacker will have the higher momentum. If we go on to the second question here, how much momentum does a 900-kilogram car moving at 50 meters per second have? That comes right from our definition, right? Momentum is mass times velocity. We multiply our 900 kilograms by our 50 meters per second, and we come up with 45,000 kilogram meters per second. So I want to take a moment to pause here and say, note the units we're using here, kilogram meters per second. We don't have a special unit for momentum like we did for energy. Right? Energy we measured in newtons, and we had a unit for it. Now, if we broke that newtons down into its base units, it was kilogram meters per second squared. We just don't have that same concept of a newton, that corresponding unit for momentum. Right? So we're just going to use our base units, kilogram meters per second squared, when we're talking about momentum. Question 3, very similar to question 2, right? We just have to multiply our numbers together. 1,800 kilograms, 25 meters per second gives you 45,000 kilogram meters per second. What I do want you to see between question 2 and 3 here, it's probably obvious, but I really want to make sure you see it. Take a moment to think about it. What did we do here? We had a 900 kilogram car in question 2. We have an 1,800 kilogram truck. So the truck is twice as heavy. We doubled our mass between problems 2 and 3. But what did we do with our velocity? Right? Our velocity was 50. It went down to 25. So we halved our mass. If we double our we halved our velocity rather. If we double our mass and halve our velocity, you see we have the same momentum, 45,000 kilogram meters per second squared in both cases. All right. So just let's take a moment, think about that. Right. P equals mv, double m, you have to take half of your v. Just getting into that relationship, making you think a little bit more. That's a multiplicative relationship. Let's look at our final question here. And it says, in order to have the same amount of momentum as a 20-kilogram dog walking at 3 meters per second, how fast would a 4-kilogram cat have to walk? Well, the first thing we have to figure out is how much momentum does the dog have? And that's easy. Take its mass times its velocity, 20 kilograms times 3 meters per second, and you're going to end up with 60 kilogram meters per second. So if the cat's going to have that same momentum, we just have to rearrange our momentum equation. We're going to say, what's the velocity of the cat? Right? The velocity of the cat's going to be its momentum. I just took the momentum equation here, 60 kilogram meters per second. That's what our dog was. We're going to say we want the cat to be the same momentum, mv. So 4 kilograms is our cat's mass. What's the velocity of our cat then? We can just rearrange our equation. We see 60 kilogram meters per second divided by 4 kilograms tells us our cat has to be moving at 15 meters per second. Again, hopefully obvious, right? The cat is 1/5 the mass of the dog, so it must be moving 5 times as fast as the dog. 3 meters per second times 5 gives you 15. So now that we've finished a few quick example problems to get our brains refreshed and working again on momentum, let's talk about the second part of our topic for today. And that is collisions. Right, so collisions and momentum are heavily related. And we need to talk about different kinds of collisions here before we go on. When I use the term elastic collision, what I want you to think about like a rubber band. We think of rubber bands being elastic, right? So we can take our rubber band, we can stretch it, and it'll come back. Right? It comes back. So that the energy that we put into the rubber band to stretch it comes back when we release it. Right? The rubber band returns to its initial shape. Another way of saying that is that the kinetic energy is conserved. Right? If we stretch it out and we let it come back, that kinetic energy is conserved. Elastic collisions conserve kinetic energy. Let's think about that a little bit. I'll give you a couple examples. If any of you play pool or billiards, as it used to be called in the old days, right, when those balls hit each other, the energy is conserved. The kinetic energy right before the two balls hit is equal to the same kinetic energy right after the two balls collide. Right. What we see is slowing down is really friction between the pool ball, the billiard ball, and the felt surface of the table. It's not the collision itself that slows down those balls. Another example would be bouncy balls. At least when I was younger, I called them super balls. But if you think about those, these are the balls. They're not super hard. They're solid, and you can squish them a little bit. But when you drop it, say if I dropped it from right here, when the ball would hit the ground, it would come back most of the way up. Pretty doggone close to most of the way up. Not quite. And what that shows you is that the kinetic energy, most of the kinetic energy that the ball had, it isn't lost when it collides with the floor because it comes almost all the way back up to your hand. So a little bit's lost. That's why I say it comes close, but they're not too bad. I want to compare that to, like, say, a tennis ball, right? If you drop the tennis ball from the same height, it'll bounce off the floor, but it doesn't bounce very far compared to a bouncy ball or a super ball. Right? And that leads us into our second type of collisions. And these are what we call inelastic collisions. In these cases, the kinetic energy is not conserved. Not conserved. Now notice I'm choosing my word carefully here. I'm saying kinetic energy is not conserved. I'm not saying that energy is not conserved. The total energy is still the same. Just in an inelastic collision, some of that kinetic energy gets converted into a different form of energy. Typically, that form of energy is heat. That heat is due to the friction. When the tennis ball, for example, hits the ground, it deforms, it compresses, and that causes friction inside of the tennis ball, which then heats up the tennis ball. So that heat is carrying away some of the kinetic energy. Right? So if you actually took a tennis ball and you squeezed it several times really fast, you actually feel it warm up, right? Because it's some of that kinetic energy due to the friction of the squeezing, of the compression. Another thing, so some other examples here, right, besides the kinetic energy not being conserved, right, we think about some examples would be a car crash. Right? So if two cars run into each other, it's very rare. You don't see those two cars bounce off of each other more often than not. I mean, they bounce some, but they don't bounce off of each other like a billiard ball does, a pool ball does. Typically, the cars will crunch up, right? And the reason they're going to crunch up is the cars have been designed. They're trying to absorb some of that kinetic energy so that our bodies don't have to take all that kinetic energy, so that when we hit the steering wheel or we hit something else, our body isn't the one absorbing that kinetic energy, because human bodies aren't really good at absorbing kinetic energy. We're very fragile in that respect. So where we have the cars crunch, the cars compress, they get all crunched up, a lot of that kinetic energy gets absorbed in deforming the material. Right? Some of it's heat, some of it's deformation, changing the shape of something. Right? We know it takes energy to, like, take a thick wire and bend it. It takes a lot of energy to do that. So it's absorbing some of that energy. Another part of the energy there is really sound, right? Two cars run into each other. That makes a heck of a loud noise. Noise has energy. Sound has energy. So some of the kinetic energy of the moving cars gets converted into noise, sound. Now, just that happens a little bit in my examples of above with the billiard balls, right? They make a nice smacking sound when they hit each other, but there's not very much energy that's actually going into the sound energy in that case. So two kinds of collisions: elastic, kinetic energy is conserved; inelastic, kinetic energy is not conserved. We're going to combine that with something you've heard before, I hope: the law of conservation of momentum. In any type of collision, whether it's inelastic or elastic, doesn't matter. The total momentum of the system is always conserved. Always conserved. Always stays the same. Quick example of this in our problem below. 1,100 kilogram car driving east at 15 meters per second collides head on with a car driving west at 25 meters per second, and the car weighs 1,400 kilograms. So this is our before or our initial scenario. What's the momentum of the system after the collision? Well, the law of conservation of momentum tells us what? That our initial momentum has to equal our final momentum. So let's calculate the initial momentum here. We had an 1,100 kilogram car. Let me do this way. We had an 1,100 kilogram car. Right, traveling 15 meters per second. We had another car, 1,400 kilograms, traveling 25 meters per second. Do our math here, MV of the car 1, MV of car 2. We have a total momentum of 51,500 kilogram meters per second. And again, our law of conservation of momentum tells us what? It tells us that the initial momentum is equal to the final momentum. So our final momentum of the system is also 51,500 kilogram meters per second. Well, that ends our lecture for today. Let's now move on to some practice problems. So our first homework problem here that we're going to look at, again, we're talking about momentum and collisions. And our first one's pretty straightforward. Who has more momentum? The 1,500 kilogram toddler running at 4 meters per second or 70 kilogram woman walking at 1 meters per second? We just have to do our math, right? What's the momentum of the toddler? Mass times velocity, 15 kilograms times 4 meters per second. We get 60 kilogram meters per second. Right? Do the same thing for the woman. We see it, her momentum is 70 kilogram meters per second. So yeah, the woman has more momentum. And the thing I'm really trying to drive home on some of this, just because something's moving faster, like our toddler here is moving faster, doesn't mean it has more momentum. Right? We could have a more massive object moving slower, and yet that slower moving object can have more momentum. If we look at question 2, in order to have the same amount of momentum as a 5,000 kilogram truck driving 20 meters a second, how fast would a 700 kilogram car need to drive? Well, again, the first thing we need to do, how much momentum does that truck have? 5,000 kilograms, 20 meters per second, we have 100,000 kilogram meters per second. Well, if we know what the momentum is, and we're going to say that our 700 kilogram car also has that same momentum, we just want to find its velocity, we can take our momentum equation, we're just going to rearrange it. Right? I'm going to divide both sides by m, and we're left with what? Velocity is momentum divided by mass. Take our 100,000 kilogram momentum divided by our 700 kilogram mass, and we see that our car must be traveling at 143 meters per second to have the same momentum as that 5,000 kilogram truck. Look at that, 7 times faster that car is going to have. That's why driving on the highway, semis are a bit dangerous. They're so much more massive, right? They have a lot more momentum. Explain the difference between elastic and inelastic collisions. The thing I really want you to get out of that, elastic collisions conserve kinetic energy. Always conserve kinetic energy. So when we're solving problems with elastic collisions, we can take advantage of that fact. Kinetic energy is conserved. If it's an inelastic collision, we can't use that because we know kinetic energy is not conserved. Some of that kinetic energy gets turned into another form of energy during an inelastic collision. Let's take that and make it a little bit harder here. So this one's going to be much more of a thinker type of a question, at least the second 2 parts. So our question says immediately after collision with each other, bouncing off of each other. So we're going to take bouncing and we're going to treat that as meaning elastic. A 1,500 kilogram Toyota Camry moves south at 2 meters per second, and the 1,300 kilogram Volkswagen Jetta moves north. So what was the momentum of the system before the collision? Conservation of momentum tells us what? It tells us that the initial momentum is the same as the final momentum. Well, what's the final momentum here? It gave us the information. We can calculate it. Our final momentum is simply the sum of the momentum of the truck with the momentum of the Volkswagen. Momentum of the truck, M times V, 1,500 kilograms. The truck, momentum of the Toyota, 1,500 kilograms, negative 2 meters per second. It's moving south. It's moving south. So we're going to use that negative 2 meters per second. Right, negative 2 meters per second because it's moving south. And we're going to add in the momentum of the Volkswagen, 1,300 kilograms, 1 meter per second squared. And we come up with negative 1,700 kilogram meters per second. And remember, we talked about momentum being a vector quantity. So this is telling us it's negative. Our momentum here, our total momentum, is in the south direction, in the negative direction. Now, the next part of our question gets a little bit more interesting. We have to think about this one a little bit more. So hang with me. Which car had more momentum before the collision? Let's think about this a little bit. We know that the momentum before and after the collision, negative 1,700 kilogram meters per second. So we know that our momentum has a southern direction. A southern direction. So if we want to think about which car had more momentum before the collision, let's think about this a little bit more. When the problem tells us the cars bounced off of each other, that means it was an elastic collision. An elastic collision. If it's elastic collision, let's try this. We can assume that the cars were traveling in opposite directions prior to the collision. In other words, right, they're going like this. One's coming north, one's coming south. They hit each other and they bounce back in opposite directions. So what does that mean? That means before the collision, our Toyota was traveling north and our Volkswagen was traveling south. Well, what do we know about our total momentum? Our total momentum is in the southerly direction. How can our momentum be in the southerly direction if the Toyota is traveling north and the Volkswagen traveling south? That tells us the Volkswagen traveling south must have had more momentum. The Volkswagen traveling south must have had more momentum because it's the only one that had a southerly momentum, and our total momentum was also southerly. Now, is it possible to determine which car was going faster before the collision? And yes, it is. Yes, it is. I want you to think about this again. We'll do the math later on if we get farther in this unit, but I just need you to think about this a little bit. We know the Toyota was traveling south. We know the Volkswagen was traveling north. We know the net momentum, the total momentum of our system is to the south. And we found that meant the Volkswagen had to have more momentum. Well, if the Volkswagen has more momentum, that means it has to have, then it has more momentum just in magnitude, more momentum than the Toyota. The only way a Volkswagen could have more momentum is if it's traveling faster. So therefore, we know that our lighter Volkswagen, less mass but higher momentum, it must have had a larger velocity than our Toyota. And we'll see a little bit later on in this unit how we can go through and we calculate that. And we find out that it's actually a pretty good number, multiple of more. Okay. Just want you guys to get used to thinking about collision problems and momentum problems. We're going to build on this more over the next few days and for the rest of the unit. Hope this makes sense, guys. If not, please rewatch parts of the video that you found confusing. And if you still have questions, send me an email, reach out to me. We can either communicate via email or I can set up a Google Meet. Or for those of you that are at school, we can meet during 3rd, 4th, or 8th periods, as well as before or after school. I really want to help you guys make sure you learn this stuff. All right, guys. Thank you very much for joining me today. Have a good day. We'll see you tomorrow.